All right, let's begin. Shall we start? Yep. All right, so first thing on our agenda is our weekly check-in. It should say week 11, not week 10. Let me just fix that. Okay, go into our content. Our first thing that we're going to chit-chat about is our random question for this week, which is about would you rather be too hot or too cold? Person answering that question today is going to be Mime. You rather be too cold? How many people said too cold is their answer? The vast majority of people. Interesting. How many said too warm or too hot? Just very shyly putting up hands. Why too cold? You don't like being hot? Yeah. I find that it's really hard to cool yourself down when you're too hot. Whereas if you're too cold, it's very easy just to layer up. And I feel like sitting in front of a heater is like nicer than sitting in front of an air conditioner. I feel like an air conditioner takes a long time to cool you down. And also being too hot means that it could also be humid as well. And humidity is a hard thing to deal with. So I'm not surprised that most people picked too cold. It's interesting. That's why we do these random questions, just to kind of see where we are as a class and people's opinions. I love to hear it. And then micro goal for this week, person answering that question today is going to be Evelina.
Sorry, to finish my history research.
Finish your history research. Yeah, I'm guessing this must be a busy week for you guys because it's last week of term, so you probably have some internals due. The good news with chemistry, though, is we don't have anything due this term, so you still have some time to kind of wrap your head around it. And in fact, we're doing an external, so we still got lots of time to learn organic chemistry. All right, anybody have anything they want to add before we move on? We're good to go? I know a couple of you guys noticed my eye patch. I decided it'd be fun to be a pirate. No, I just had a little eye infection. I'll go to the doctor today, but just because I know some people were concerned. That's why I look like this. Anyway.
Guys, get your bowl forms. It's at the office.
Oh yes, that's a good announcement from our head girl. Don't forget about your ball forms. This is the last week, so you need to get those forms handed in and also pay your $50 deposit.
And you guys performance.
Yep. Hopefully we're in orange when you guys have your ball.
You don't have to be months anyway.
I thought there was a number restriction though for 200.
Yeah, the number restriction is 200.
Yeah.
Jason, coming in, you have to wear your mask, but when you're inside the hole, you can take it off.
Okay, that's good.
Yeah.
All right. All right, cool. So, learning journey. Last week we talked about techniques. We also talked about the amines, the amides, and the acid chlorides. For today, we are going to do our final functional group, which is our esters. So we'll define them, and we'll also explore how to name them and create them, and some of their properties as well. So that's what's on our agenda. Last thing before we start with the notes is our weekly fakatoki. This week is He Ihu Kure He Tangata Hare, which is as a dog follows a scent, a traveler relies on the hospitality of others. Beware blindly following your nose. Be deliberate. Make good choices. I think that's a great one to have for an end of term week. Make some really good choices because you are probably finishing up a lot of assessments. You might need to prioritize some of your time as well to make sure you get your assessments done. So just kind of keep that in mind. I'm happy if chemistry gets put on the back burner because I'm mindful of other subjects needing to take priority because we don't have anything that's due anytime soon. All right, lesson plan is actually really, really short today, which is great. I'm going to start by giving you guys the Ester Notes, and then you guys have the rest of the period as a Mahi Choice. So you guys can choose what you want to work on. And the Mahi Choice is all related to the ester material. Cool? All right, we are doing number 1 off our checklist, and G, which is the esters, just the same old things before. Does anybody need a booklet of notes because they didn't get one the other week? Anybody want a booklet of the PowerPoint notes? Anybody else? Fire away. Need one of these? People would like one of these? How to? All right, cool. Let's talk about part 2 then. So, here's my little Ester joke. So, how is exactly an ester produced? Well, an ester is produced by condensation of an alcohol and a carboxylic acid. And don't worry, it's all right. Organic chemistry is hard for everyone. Little thing that was to kind of get us started. Let me get some paper because I'm going to be writing on some examples. All right. So let's start with what are esters and how do we make them. The first thing we are thinking about is the reactivity of alcohols. So what happens when I'm trying to create an ester is that I react an alcohol either with a carboxylic acid or with an acid chloride. It's much easier for me to do this reaction with an acid chloride because we know that acid chlorides are really reactive organic molecules. What you're looking at for your esters is you are looking for a carbon that has a carbonyl and also has a single bonded oxygen. So this functional group here that I'm circling around, that is your ester functional group. What you'll notice with your ester functional group is that you're gonna have two carbon chains. This red carbon chain is coming from either your acid chloride or carboxylic acid. That makes sense because you have the carbonyl. And then the green carbon chain is coming from your alcohol. So we're basically combining two functional groups together to make our ester. In this case, the byproduct is going to be a hydrochloric acid. Sorry, something went down the wrong pipe. So that comes from your chlorine and then also the hydrogen from the alcohol component. Are we okay with that so far? So that's how we make these guys. The abbreviation for this functional group is COO, representing a carbonyl and a single bonded oxygen. Just be mindful that you have one carbon that has the carbon double bond and the single carbon, and then the second carbon will only have that one oxygen attached to it. So here are some examples of esters that we can see, and like I said, it's basically like the carbon chain has gotten interrupted with an oxygen. Are we okay with that so far? Of what is ester? All right, so here comes then the trick when it comes to naming the esters. So since I have two organic chains, I need to be really mindful about how I name them because there's both what was an alcohol and a carboxylic acid. So one of these guys becomes essentially a branch, and then the other one becomes the parent chain. We saw this with the amides, if you guys remember. The alcohol component is the one that becomes the first bit of the name and thus is the branch. And then the second part is what's going to be the parent chain. That comes from the acid component. What did I have to add about this as a reminder? I'm trying to think. Be really mindful that you get this the right way around because then you swap the molecule around if you do get it the wrong way around. The other thing that I see as a common mistake is that people count very quickly and they forget to count the carbon that has the carbonyl. So make sure you count this as 1, 2, that sort of thing. The nice thing about esters is that you don't need to specify the number of which the ester is on because the name itself will describe how many carbons are attached to each end of the ester. Cool. And basically what we're looking at is the ester is written as two words. You have your branch component and then you have your parent chain, which has come from the carboxylic acid. Shall I show you what I mean or just point out with this guy each one? All right, so you see how in this organic molecule I have one carbon attached to the oxygen and then I have a carbonyl and another carbon there. So this here comes from the comes from the alcohol component. We can see that this carbon only has a single bond to that oxygen. So that coming from my alcohol goes to the first part of my name, thus the methyl. This part here is coming from my carboxylic acid. I know it's come from the carboxylic acid component because of the carbonyl, the C double bond O, and I count it. 1, 2. So then that is my parent chain. That's where I'm getting the F. O8 is how we do the suffix for our esters. So it becomes methyl ethanoate. If I called it ethyl methanoate, then what would happen is that I would only have the one carbon here and the two carbons on the other end. So this one's slightly different from most of them that we've learned because it's not the longest chain. And we'll actually see that with our next, or no, we don't see that in the next example. Next example, the longest chain is still the parent, or the carboxylic acid. All right, here's ethyl propanoate. So ethyl, this is our alcohol group, and we see there's 1, 2 carbons, and then propanoate, prop 1, 2, 3. That's where that's coming from. The trick is to look for the carbonyl, and that will help you distinguish what side is which. You also don't need to write it in this order, so you can write it with the alcohol component coming first and then the carboxylic acid. Do you want me to draw it so you see what I mean?
Yeah.
All right, just so that way you know. Do you want me to do like a brand new example just so you guys can see?
Yeah.
Okay. So, let's do C, double bond O. I know it's laggy, doesn't it? 1, 2, 3, 4. Okay. So here's my first example. I've drawn it this way, and when I'm looking at it, I'm looking for the carbonyl, because that carbonyl there tells me that this has come from the carboxylic acid, and thus that's going to be my parent. The single bonded oxygen, this here has come from my alcohol. So that's going to be my branch. Are we good so far?
Yeah.
All right, so when I go to name it, I see that this is 1, 2, 3. So I go propyl, and then I see this is 1, 2. And this is an example of how the branch is actually a longer chain than the parent chain. And that's okay in this example because what we're looking for is to name the alcohol component first and then the carboxylic acid. So it'll be propyl ethanoate. We got it? All right. If you draw your carboxylic acid like, or sorry, your ester like this, is that still propyl ethanoate? Yes, it is. So you can see what I'm saying? You can draw it the other way around with the alcohol coming first.
Yes.
Oh, I should include that. And then your carboxylic acid coming second, it's still the same molecule.
Because it's like can rotate.
It can rotate. You're just basically flipping around the molecule. You're still following the same naming rules, which is alcohol comes first, then the carboxylic acid component.
You don't have to number them.
You don't have to number them now. If I had drew this instead, just trying to show another example. Hopefully I did that right. If I drew this, you see how this is a different molecule because my branch here has only 2 carbons, and then the parent chain has 3 now. So when it goes to name that one, this one would be ethyl propanoate. Do you see the difference?
Yeah.
And like it's very, very minor. So it doesn't matter if you flip these two around and you have the alcohol going first and then the carboxylic acid, but it does matter how, like, where the carbonyl is and how many carbons are coming off that carbonyl, because that decides the carboxylic acid.
Yeah.
Whereas this single bonded oxygen decides what the alcohol was. Does that help with the naming?
Yeah.
It also then is how you translate the drawing as well.
Mm.
Okay? So I think the next couple of slides were just some examples of how to put esters together and how to break them apart. Let me just get the slides on my phone so that way I can keep the document camera open. Cool. So let's see some examples of how we put these bad boys together and how we break them apart. The first example is, how do I make my ester? And this is a very common question they can ask. They give you two organic molecules and they ask you to put it together. So in this case, they've asked us to put together methanoic acid and the other thing that we're putting together is propan-1-ol. So let's draw each molecule so we know what we're looking for. Propanol, or sorry, I should say propan-1-ol, is that. Whereas methanoic acid is just that. Do we agree with me so far?
Yes.
All right, so when I put these two together, what I'm going to be doing is I'm going to be removing the OH from my carboxylic acid and I'm removing the hydrogen from my alcohol, so that way these two guys, the carbon and the oxygen, can come together. Does that make sense to everybody so far? So this here is going to attach to that, and we're going to lose H2O because we've lost the OH here and we've lost the hydrogen from there. So if I was to draw my full molecule, and I'm going to keep it with the color code, that's my ester. And if I was going to name the ester, it'll be propyl methanoate. Now with that loss of water, we call this reaction quite oftenly a dehydration. Because it's dehydrating the molecule. You also might hear it as a condensation reaction because you're forming water. Are we okay with all that? I haven't gone too fast.
So is this going from a carboxylic acid to an acid?
Yeah, so this is going from a carboxylic acid and an alcohol to an ester. Let me just grab the flow chart so you guys can see. Should hopefully be on there. Once I find my flow chart. Where'd my flow chart go? Too many papers. Here it is. Here we go. So do you see how we have ester here?
Yeah.
In order to get my ester, I need to combine two things together. So either I go alcohol with carboxylic acid, or I go alcohol with acid chloride.
Oh, okay.
That's how I get to my ester. So there's two functional groups that need to come together for an ester. It's just like when we were talking with the amides. You need to have your either carboxylic acid or acid chloride plus an amine or ammonia to make your amides. So it's those two functional groups coming together. And I should probably specify on this thing, it's acid chloride or carboxylic acid plus the alcohol. Are we good? Can I keep going? Do you guys need another example? The other example I have breaks it apart.
Oh, yeah.
Would that help? Okay. I'll do the break apart and then you can decide if you guys need another one. So, in this example, I'm starting with an ester. So, and they were nice enough to give me the name. Actually, is it the same one? No, it's not. All right, we see C double bond O, CH3, O, CH 3. So if I was to name it, what would the name be?
methyl.
Methyl's correct so far, because we see that there's an O.
Methyl, ethanol.
Yeah, ethanoic, there's 1, 2. We good? All right. When it comes to splitting them apart, we're going to be looking for that ester component, so that carbonyl and that single bonded oxygen. Now, where it breaks is between the carbon and that single bonded oxygen. So this is the break point. All right. So this component here is going to go CH3, C double bond O, and what it's going to gain when it breaks is an OH. Whereas when this one breaks, it's going to get CH3O, and what it's gaining is the hydrogen. So basically, it had a water molecule. The OH goes there, and the hydrogen goes there. This is also known as hydrolysis. Because we're using water to break up the molecule. You could also call it a hydration reaction, because we've added water. Just add water. How does that sit better? Do you guys?
That's the way to take it to reverse it.
Yeah, so this is basically how to break it apart. And we'll talk about the hydrolysis in its own separate lesson, because we're going to look at acid versus base hydrolysis as well. But just as a general principle, we're looking to see where the carbonyl is and where that single bonded oxygen, and then we break where the carbon and that single bonded oxygen is. So just making sure you break at the right point. And it's always going to break there. Do you guys need another example? Or we're okay to move on?
What was taking the other ones to, what was that reaction for?
So there's several different things that we can call it. We can call it a hydration reaction. A dehydration reaction, because we're removing the water from both molecules. You could also call it a condensation reaction, because water is the byproduct. So condensation because water is a byproduct. Or dehydration because you're losing water. That's where those words come from. So you might hear me refer to things like that. Do you guys need another example? You good? Anybody else want to give their opinion? Do you need another example? No? We're okay? All right. The good news is you guys are going to have some chance to practice this at the end, so I can walk around and check. Anyway, that's your last functional group that I need to teach you. Let's talk a little bit about what they are. They're colorless liquids, so it's really hard for us to then be able to distinguish them from other organic molecules because they're all colorless. The thing about esters is that they're very volatile. They have really low melting and boiling points. And when we compare it against the carboxylic acid and the alcohol, it'll have a lower boiling point than both of those things. And the reason why is because we're losing those hydrogen bonds. When these two molecules come together, we lost that hydrogen bonding capability, which is a stronger intermolecular bond. And so less energy is going to be able to break them apart. They're also going to be extremely nonpolar as molecules because now we have carbon chains on both sides. So that's the other thing to keep a lookout for. They're not very soluble in water. Useful for us as an identification tool because it means that when I mix it with water, I should expect 2 layers. So again, if we're thinking about our identification test, my esters I will find because of their lack of solubility. The other thing is that they are not very reactive. So that's the other thing. Usually you determine an ester by process of elimination. So yeah, not very soluble. The other way you can identify esters is that they smell really sweet. They're quite a nice smell. In fact, let me show you guys a little chart because we're going to be making esters on Wednesday. Yeah, that'll be fun. Which reminds me, Wednesday, make sure you have closed-toed shoes because we do need to use concentrated sulfuric acid for the reaction to work. And if you don't have closed-toed shoes, then you can't do the practical. So right now, I'm not wearing closed-toed shoes because you can see all this area of my foot is exposed. So do be mindful that on Wednesday, I'm going to be real strict with the lab wear. But I think most of you guys will be fine. Anyway, I'll give you guys on Wednesday. We don't have all the alcohols and we don't have all the carboxylic acids. But the neat thing is that when we cross the alcohol and the carboxylic acid together, you can get things that smell like banana or pear. So yeah, there's a huge range. I think from what I've checked with the technician, we have, I think, up to butanol for our alcohol, and we have, I think, propanoic acid as our highest. So we only be able to make these guys here. But still, that's a pretty good range of stuff to play with. So, but yeah, that's what I'm saying about how esters make these really nice smells. Esters are also commonly added into perfumes. They're also commonly added as a food additive to kind of give things that banana smell or banana flavoring. Cool. That's why artificial banana doesn't taste the same as real banana. Yeah. Are we good with that so far? So the other way I can identify it would be it smells really nice. But mainly if you were identifying it, you would. So esters are produced through a process known as esterification. We can use the alcohol and a carboxylic acid to do that. However, when I do that reaction, I need to use concentrated sulfuric acid as a catalyst because the reaction doesn't happen very quickly. So that's why when we do the lab on Wednesday, we're going to be using that concentrated sulfuric acid. I could also do this reaction with an acid chloride, but why would I not give you guys acid chlorides? Because they're very reactive and dangerous. And so it's safer for me to do carboxylic acid with sulfuric acid instead. Anyway, this is an elimination reaction because I need to remove things in order to make that bond between my two organic molecules and what we are going to be removing. Depending on what the acidic component is, it's either going to be water or HCl. So if I am doing a carboxylic acid and an alcohol, I would be making a water as my byproduct. If I was using an acid chloride, then instead of having the OH being released, it would be the Cl. Cool. And this can also be classified as a substitution because we're going to be substituting out the OH for the next carbon chain. So lots of different ways you can think about it. When we do our esters, we would start with the carboxylic acid and the alcohol. We would need that sulfuric acid as the catalyst. We want to heat it to increase that rate of reaction because it's not a very fast reaction. So again, when we do this experiment on Wednesday, we will see that with hot water is what our catalyst for temperature will be. You obviously want to neutralize that sulfuric acid and any excess carboxylic acid, so you're going to need to add the sodium carbonate to neutralize it. So again, we can start seeing the techniques we talked about earlier being used in the practical in producing our ester. Cool. Esters are not water soluble, so we can use a separating funnel to remove it and separate it, but we should still purify it in distillation because that's always a good final step to make sure I have my pure ester. Are we good so far with that? Esters are really neat. They smell really, really nice for the most part, unless you get the ratios wrong and then it smells like the carboxylic acid instead. Cool? All right, I'm trying to think if there's anything else I want to add about the esters. Don't think so.
Wait, how did the carboxylic acid smell?
So carboxylic acid, some of them have scents to them. You know, like ethanoic acid is what we find as acetic acid, which is the vinegar. So that also has a scent to it. And same thing, some of the alcohols have smells to it, like when you think about hand sanitizer and stuff, that has a scent. So when you guys are making your ester, it's going to be really important that you get that ratio just right, so that way you can smell the ester and not the reactants. Does that make sense? So I know I've said this multiple times, but make sure you wear closed-toed shoes on Wednesday, so that way you can make your ester. Or not Tuesday, Wednesday. And Wednesday is just going to be a fun day for you guys just to kind of make some esters, smell some things. There's also a podcast we can listen to about perfumes, which I thought would be interesting. So, like I said, there is the alternate way to make esters, which is a lot easier using the acid chloride, and we just mix them together. I don't need to then add any catalyst like sulfuric acid. I also won't need to add any heat. It will happen automatically. But the problem is this is a lot more dangerous because the byproduct is that hydrochloric acid. Acid chlorides are very volatile, so it's very likely there's going to be enough heat to vaporize things and make them volatile, and then you might breathe it in. So if we were making esters this way, we would have to make it in the fume cupboard so that way it sucks up any of the potential vapors. But it's a very fast reaction. It's a very high reaction. There's no heat, there's no catalyst, there's nothing. So industry-wise, they probably make their esters this way because it's less reagents and less energy. But obviously in a classroom, we won't do that. And in fact, it's very hard to get your hands on any acid chloride in a classroom setting because they're so potentially dangerous. Any questions? All right, cool. So the good news is you guys basically have the rest of the period for your Mahi Choice just to sit and process. I'm happy if you guys want to work on a different subject because I know there's a lot of things due this week. I have differentiated the work, so there's some stuff with level 1. All the level 1 practice is just naming, so really good way to get started. If you're feeling a bit more confident, you can move on to some SciPad or ESA work. If you're feeling like you're really got everything down, start looking at those NCA questions. And now at this point, because you know what an ester is, you can basically do any of these questions here as well. And for this lesson, I have marked it out of 8, but if you want to get a 7 or 8 and show me excellence level, I need to see NCA answers. Cool? All right. Call me over when you have work to look at, and that's basically it for today. All right, so to summarize today's lesson, we've covered the last of our functional groups, which is the esters. You should be able to name them and talk about their properties and identify them, draw them, etc., etc. Remember, with the esters for identification, what's the word? It usually is cross-elimination, and also they smell sweet, and they're insoluble. Don't forget closed-toed shoes for Wednesday. We're going to be making esters in class. So yeah, if you're successful today, you should know your esters.
Oh, wow.